Just to begin today's lecture, this is actually the first lecture from the second half of period 2. So congratulations to all of you who are here and also more coming. We're halfway. Yeah? So the rest, I can tell you the rest is becoming a little bit more complicated, but it is also becoming less computational, especially for some of you who talk about the computational side of our lecture in last week. I'm not going to wait for the rest to come, but I'm going to give you 3 updates mainly. I think after the first half of the course, and you now revisited, try to revisit our very famous, let's say, this connection of process structure, property, and performance that I have introduced to you at day 1 on material science and engineering. Basically, we're trying to figure out what are for the core of this and what are their interactions, their kind of dependency of each other. I think we started with the structure. That is our first week topic. And with the structure, we were mainly talking about the connection between structure and property, because the properties are decided by structure. So the structure here is let's say a term across several length scales. So it's not just structure as you see with your eyes. It is also structure that you probably don't see, but you could observe from microscope, which is more or less the microstructure. And then if you go zoom in and more, you will see the atomic structure. That is the 3rd level or nano level structure. All of them will be deciding what your property, the material will be. And then we really dive in the material properties for, let me get the laser point here for you. And we dive in the material properties for our 2nd week. We talk about mainly mechanical properties, especially on fracture, on failure, let's say more general. And I think now you have very good vision about structure and properties. So I think you can imagine what we're going to talk about today or this week. So this week we're going to talk about, so not performance, but performance has already been partially covered in the previous lecture, let's say. We're going to move to the final element in this, what is this called? In this 4 elements, right? And this is going to be the process. Yeah, this is a term I think everybody has very good understanding or has some good common understanding, but you probably don't know you really understand. After this lecture, I mean this week lecture, you will get a much more systematic and theoretical understanding about the process. And before we talk about process, especially the process in our lecture, you need to get, let's say, 3 very basic knowledge about. These are the tools for us to understand process. So the first one is called diffusion. So as you can see, I tried to get a small icon for you. That is something related to atom level phenomena. And then you will need the tool which called phase diagram to understand, to be able to design your processes later on. And in the end, we will introduce you the most important thing, which is called phase transformation. Actually, this part is already part of in the phase diagram, but it's not systematic. We will have the phase transformation covered tomorrow. With all this kind of prerequisites, you will be able to finally get the understanding of processes and how to use different processes to do something. All right, that's the basic introduction for our lecture in this week. And without further ado, we will start with the diffusion directly. So diffusion is something I think everybody is very familiar. Here I'm giving an example. I forgot, I think that was a hobby from, I think it's not only somebody, one's hobby, that was something mentioned by Daniel probably in our first lecture. The hobby is to take coffee. I think most of you have this hobby. And if you take just the blank coffee, this is not so relevant for you. But if you are taking coffee with sugar or milk, and you will see the phenomena of diffusion every day. So basically, the whole process of this thing, you try to get the sugar in your coffee homogeneously is called diffusion, right? So, but we need a proper definition. What is diffusion? This is always how we start a course. We gave the definition, and we try to understand the mechanisms of why diffusion is happening. Well, you will get partially the mechanism because let's say the deep down mechanism is very sophisticated, although it's such an easy phenomena. The always difficult answers is always related to the very easy phenomena. We will not cover here. That is an answer you should seek in the thermodynamics lecture. And the third one is, let's say, more practical. If we learn it, and what is diffusion used for? Why do we learn it? Yeah, we learn it for a specific application, although not always, but sometimes we seek for its application. And those are the, let's say, the qualitative side of the course. Then we're going to move to the quantitative side. So how do we describe diffusion with what equations? And of course, in the end, what factors, external factor will influence the diffusion? So this will be the 5 leading questions for our diffusion session. You could think about it. And this probably is also the part that we always, the kind of structure or methodology we're always taking for our lecture, if you just recall what we have done before. What I add as a new slide here is to give you a, let's say, learning objectives. I think you're probably familiar with this. Well, I'm not a big fan of this, to be honest, because I'm going to give you terms that you don't know. But this probably is a good chance for you to see what terms you will know after the lecture. So the first learning objective is, after the course, you should be able to name and describe the 2 atomic mechanisms of diffusion. So now it's also the answer revealing part. So the diffusion deep down is atomic motion or atomic related mechanism. And the second objective is to be able to distinguish between steady state and non-steady state diffusion, so 2 types. And the third one is to be able to write the fixed first law and the second law in equation form, and you will be able to define the parameters of them and note their applicability. And the last one is to be able to write the solution to the fixed second law. So you will see what I'm really talking about. And because the second law is a equation, is a differential equation, it is not something you can solve directly. You first need to solve that to get a solution equation, and then you can use it. Yeah, then you should be able to write the solution to the fixed second law for diffusion into a certain condition, which is the semi-infinite solid with the concentration of diffusion spaces and surface is a constant. So you have no clue what this is about, but you will learn what this is about. And finally, you will be able to define those parameters. The last objective is to be able to calculate the diffusion coefficient for some materials at the specific temperature. Yeah, I think these are the 5 objectives with a lot of new terms. Now we're going to go and explore what this term's about. First of all, what is diffusion? And before I gave the diffusion, you see it already at the moment, but I first gave you a figure. I think most of you should be familiar with this figure. This is something we have learned probably in the high school or junior high school. And this is called the Brown motion, right? Or Brownian motion. And this is, not, of course, not an observation. This is a simulation. Basically, if you just pay attention, first we have two particles or two atoms at the center of this gas atoms. And soon after, these two were just going everywhere into the space. You can see now the blue curve is noting their kind of a path. And this is already something called diffusion, right? Because you put two items together into a bunch of atoms, and suddenly they kind of disappear, or they're kind of moving around. And this is called diffusion. And this is even one of the mechanisms of diffusion. So now you can understand that diffusion deep down is a mass transportation by atomic motion. So something you probably also observe when, I mean, now it's difficult, but if you just try to have in a sunshine day and try to watch what is happening, especially when you have just a slice of the sunshine, you will see the dusk moving in the air. And I mean, the dusk is a little bit heavier than the air, right? Definitely. But you will see all the dust, they're not just dropping, they're just going anywhere. So the explanation is exactly what we're saying here. The dusk itself is, let's say, not something, because it's something you could see. It's not atom. But what you don't see is the air atoms, is the gas atoms. They're just bunching your dusk, and the dusk is really going anywhere. Randomly. So that is the diffusion by definition. So deep down, it's atomic motion. And two mechanisms, they're distinguished between gas and liquids. That's one, and the second one is solids. So for gas and liquids, I think you know that is by the famous Brownian motion. And for solids, I think most of you probably are not so familiar. For solids, the diffusion is achieved by vacancy diffusion or interstitial diffusion. So with the knowledge we had from the lecture 1, you should be able to know vacancy diffusion is also something called, let's say, it can be substitutional diffusion, very much related. And the interstitial diffusion is something you have to see with the interstitial positions of our crystal structure. You will see all this in detail. And the two diffusion types, so we could kind of distinguish the diffusion with different criterion. This is one criterion. The criterion is if you are diffusion two atoms from two different materials, or your diffusion just several atoms of one material. So the first one is called interdiffusion, when you try to combine A and B with different materials, and the second one is called self-diffusion. It is a atomic migration in pure metal. So this is a first, some basic ideas about diffusion. Let me move forward. So we said we have two types. The first is interdiffusion. So this is an example for the interdiffusion for solids. Now what we are trying to mix is material A and material B. So at the left-hand side, you see before diffusion. So this is A and B. What you could probably already imagine the driving force for this interdiffusion is basically what? Yeah. So you see it is basically the concentration. So the atoms trying to go from the high concentration to low concentration, right? So at the beginning, we have 100% of A on the left side and 100% of B on the right side. After diffusion, basically the A and B are trying mixing, and they try to go from the high concentration side to the low concentration side. And I'm giving you this as, let's say, a mechanism or as a kind of rule, but the deep down reason for this is very complicated. And that is related to the second law of thermodynamics. Probably, I think, remember, Alexei has mentioned before, this is really going to the why we're having the entropy always bigger than 0. But I think your common sense would tell you that diffusion goes from high concentration to low concentration. So this is clear. What is probably not that easy to realize, and the self-diffusion is something happening between the atoms, just the migration from one place to another. You don't realize it because the material macroscopically has no change. But if you just look at microscopically, the atoms, they're just swapping their positions. So even for solids, for liquids or gases, you're clear seeing what is happening with the Brownian motion. For solids, you don't see it, but it is happening. So the atoms are not always staying the place as they were initially are. Yeah. So if you just have some certain knowledge about thermodynamics, you would understand, right? If there's temperature, the atoms are not sealed. And now you probably would wondering, for both of them, for both interdiffusion and self-diffusion of the solids, how we could diffuse, for example, this atom C initially here. So there's a magic word, he just swapped with another one here. So the answer is the diffusion is finally realized by vacancy movement, so, or vacancy diffusion. So how to understand this? You probably remember in our metals or crystals, there are always vacancies. Yeah? That is the basic formation of dislocations and also other effects. And diffusion happens, so now I'm giving an example of interdiffusion, but this applies also for self-diffusion. It happens between the first exchange between the atom with the vacancy. Yeah, so you can see this atom first is changed with this vacancy, and now diffusion happens, right? This atom is in, the A is in your B matrix, and the next one from A will interchange with the diffusion, with the vacancy now in A, and finally this part is the vacancy comes up. You can imagine now this B atom could easily get into the A matrix. So this very simple animation actually tells you the mechanism of diffusion happening in solids. As you can see, two decisive factors. The first one is the number of vacancies. So if you remember our equation long time ago, now let me ask someone, what decides the vacancy density or the vacancy fraction in our material? I'm trying to get some for you. It's a time to get some refresh. You probably remember the vacancy density is decided by temperature. Of course, it's something else, but temperature is the key. If you have absolutely 0 temperature, your crystal will be ideal. You will have no vacancies. But of course, nothing is possible over there. And that's why you always have the vacancy. That's why you always have a high number of vacancies when you have higher temperature. So that also explains you a kind of equation later on I'm going to introduce you. So with these two topics, you can already understand if you have a high number of vacancies, especially let's say with higher temperature, you will have what? Better, higher diffusion rate. Yeah. And the
makes sense
term that's gonna kind of decides your diffusion rate will be the activation energy to exchange. You could understand when we do the exchange, it requires some energy. Yeah? Nothing is happening without energy. We're not going to talk about that in detail. That is, again, too much related to your thermodynamics. Let me ask some of you, did you learn anything about thermodynamics? Hey, Drew, did you learn anything about thermodynamics in your first year course at Otto?
Did you call my name?
Yeah.
I think we're gonna learn that this year or next year. I'm not sure, but not yet. We haven't learned.
Oh, you haven't learned anything about thermodynamics, yeah? Okay.
No, I don't think so.
Good. All right. So that was not a very good arrangement. It is better that you have some knowledge, but it's also okay because now we're just introducing you phenomena terms in a very broad spectrum. And when you go to thermodynamics, you will be able to learn, first of all, why diffusion is happening, why it is driven by the concentration, and what is this activation energy is about. Excellent. That was vacancy diffusion. And now let's talk about interstitial diffusion. So that is even easier for you to understand after we talk about the vacancy diffusion. This happens when you have, let's say, a diffusion between a big element, or not necessarily big elements, but it's always happening when you have a small atoms diffusion into another material, because you probably remember our crystals are always in a certain structure, BCC, FCC, and there's always spaces for small atoms to go into. Yeah? So those places were called interstitial places. And for example, here, this small atom, they can just come into this position, and they can easily also go around into these positions. Now you can understand for this type of diffusion, you would have much more, let's say, vacancies for your material, because you don't need to count all the real vacancy. All the interstitial places are your vacancies. And this diffusion will happen much more rapid than what we have with vacancy diffusion. So those are the two diffusion mechanisms. And as I promised, I want to tell you what is diffusion could be used for. So this is a very good example for you to learn. The diffusion can be used to do a case hardening. Why I'm giving this example again, because it is something we have brought up before. So first of all, what is case hardening? So this is a typical process, let's say, applied to, especially for the gears, which is used in engines or in the transmission in automotive cars. Yeah? And we want to have a very strong surface of the gears, right? And this is realized by so-called case hardening. Basically, we're trying to get some diffusion of the carbon, so especially carbon atoms, because they're small, and they're gonna just diffuse into the steel in the atmosphere, and this carbon in the steel will basically make the steel much harder. As you can imagine, this is also one of the ways to increase the fatigue life, if you remember, because it will create some compressive stresses on the surface, which is going to go improve your resistance to fatigue. Yeah, so that is a good application of diffusion. Now let's move to some quantitative description about diffusion. So this will, here we're going to talk about basically three important equations. And the first one is more related to the diffusion itself. So as you can see, diffusion is a time-dependent process. Yeah, it takes time for all the atoms, either vacancy or interstitial diffusion. They will take time to really get it done. And that's why we're going to use a time-related measure to describe our diffusion. So this is about the rate of diffusion. So this is nothing about velocity. This is nothing too different than velocity. So velocity is describing the rate of your movement from A to B, right? Now we're trying to evaluate the rate of diffusion, but diffusion is not just one atom to the other, it's a bunch of atoms. That's why we have to introduce a new quantity, which is called diffusion flux, which is indicated by J. And how is this defined? So the definition is also simple. It's defined by the mass of diffused species over a certain area and over a certain time. So that is that is quite simple to understand. So why is the flux? Because we need to involve area, right? As you just specifying something over time, it is not purely indicating about diffusion, because diffusion could happen in a large place or in a small place. So that's why we have to introduce area as well. So to express it into, let's say, quantities, it's m over a and t. So the unit is kilogram over meter squared and times second. All right, how do we measure this? Actually, to measure it is pretty simple. Basically, you just need to use especially for the interdiffusion, you use a thin sheet or Mabron. Try to separate your material A and B, and then you just try to measure how many A go to the B places, and or let's say the change of the mass from A to B, and then you can just calculate this versus time. Basically, of course, this is the slope, which include the 1 over A as well, right? But you will see the flux basically is proportional to your slope of mass over time. So this is a very easy equation for you to know to define the diffusion flux. And now I'm giving you two very classic diffusion types. This is not all, this is even far from all, because they're ideal. So you only use it to understand those quantities, understand how you want to describe it, but most likely you will find they cannot really describe anything in practical. They can only describe things ideally. But this is our starting point. Yeah, we always start with ideal cases. The first thing called steady state diffusion. So what does that mean? The steady state, I think you can understand, guess it. It means your rate of diffusion, basically the flux, is independent of time. So this is ideal because basically you will have your diffusion like constantly. Yeah. So you have your concentration on the left side and concentration on the right side, and they stay constant. And then the diffusion is happening like constant without the evolution of time. So you probably know this is far away from reality, because in reality your diffusion always trying to get a certain state, right? But now we just try to understand it. Let's assume you have a constant A always, constant B always, and the flux is always as it is. And we can get one description about diffusion, which is the flux is dependent on the concentration gradient. So the gradient is nothing but the slope. So it's about dc over dx, because we have a certain distance to allow the diffusion to happen. And if we just make assumption, so just remember this assumption, this is not always true. This doesn't need to be true for the steady state diffusion, because here I draw a line between this delta x, so this place, and between these two concentrations. It can also be a nonlinear curve. Yeah, it can be anything. As long as this curve does not change with respect to time, then you have a steady state diffusion. Yeah. But let's make it even simpler. So let's assume we have a linear case. Basically, in that case, we can make this infinite small dc over dx becomes delta c over delta x. Right? So in the end, it's going to be c1 minus c2 over x2 minus x1, right? Because it's line. So then you can finally write your fixed first law. So this is like J is equal to minus D times dc over dx. So if we just make it simpler, it's going to be delta c over delta x. And here, the D is so-called diffusion coefficient. I think nowadays you are all familiar with such a thing. This is basically the logic for us to discover any phenomena. So we try to first clarify the interdependency like this, like Mr. Newton did. And then we try to introduce a constant to give a quantitative correlation. So this is the minus D. The minus D is just to indicate the diffusion is opposite to your gradient. So if the gradient is from high to low, and the diffusion is going to go opposite of that. And the D is always positive in that case. That is the fixed first law. I hope that is clear because it's pretty simple. The second law will be a little bit more complicated. As you can imagine, we talk about the steady state. Now what we need to talk about is non-steady state. This is also easy to understand. The non-steady state, which is a little bit more clear to the reality, the diffusion changes with respect to time. Yeah, so the concentration of the either A sign or B sign will be dependent not only their position, it will be also dependent on the time. So that is the non-steady state diffusion. So this is really a general definition for almost all the diffusion in our daily life in the practice. And this is described by the famous second fixed law. And now it is already something quite complicated. This is described by a differential equation, even a second order differential equation. So the dc over dt is equal to d again. So the diffusion coefficient, then it's proportional to what? To the second derivative of concentration over positions. Yeah. I guess everybody has learned calculus, so you should be able to get the sense of the equation. So this equation will involve three variables: concentration, time, and position. So these three variables with one differential equations. You can get a good derivation about this equation as well, but this is not going to be explained in our course. You basically take it as it is. You know it. I will not also ask you to memorize this, but you should be able to find it. You should be able to understand it. That's the main condition. But this doesn't tell you anything specific, because in the end, when we talk about diffusion, we want to know after a certain time at a certain position, what is the concentration, right? So that's why you know after a certain time of mechanical disturbation, you will dissolve your sugar into the coffee. It doesn't happen immediately, it happens with a certain time. You probably want to know what is the time, yeah. And this is our goal. But with such equation, you cannot get that. You only know, okay, the concentration gradient over time is related to the second derivative of the concentration over position. So how should I do, right? I think this is a concept you guys are very familiar with. To solve a differential equation, you need boundary conditions. Yeah. And that's the only way you could solve it. especially a differential equation with three quantities, three variables. And how do we do this? So here I'm giving you again an ideal case. It's not that ideal as the steady state case, but it's more or less like that either. So basically we have two assumptions. The first assumption is we're having a surface concentration as a constant. So you can imagine they're copper atoms, and now you want to kind of diffuse your copper atoms into an infinity bar, whatever it is. So what will happen? So these are the two assumptions. The first assumption is the surface gradient is surface concentration is a constant, and the second is your diffusion into the infinity space to the right. So if you just described it mathematically, so here you have Cs, the surface concentration of copper atoms, and then you have the C0, which is the indicating the concentration of your medium, the infinity medium. So for such a non-steady state, it's a special non-steady state diffusion. You could write two boundary equations or boundary conditions. The first one at time t, and the position from 0 to infinity, you always have the concentration equal to C0. So basically, I'm giving you the profile of here, this red line. And when we have diffusion when time is bigger than t, you will have a diffusion looking like that. So T1, T2, T3, right? But the common feature is at position 0, the concentration is always equal to Cs. That's what I said about the first assumption. You have a constant concentration first here. And the second for T over T bigger than 0, right? But it's the third in total. Boundary condition is the C is gonna be C0, but now it's not from 0 to infinity. It is at infinity. We will have always C0. So as you can see, now we have three boundary conditions, three boundary equations. If you are good at mathematics, if you're good at calculus, you will be able to solve this equation, to solve that differential equation I showed you, the fixed second law. And you will arrive at such an equation. So this is the solution equation of fixed second law. So just remember, guys, the fixed second law is a general equation. It's a universal equation. The non-steady state equation here, this solution equation to fixed second law, this is a specific case when we have this specific non-steady state, as I just described it before. So don't get confused with that. If you have another non-steady state, you will be able to define another set of boundary equations, and you can solve your fixed second law in a completely different way. So this is what we solved. Actually, it's easy to understand if you just imagine what will happen. The curves in the last slide is already giving you the trend, and here I'm drawing it again. So the diffusion will just happen like that, right? With the time, you will get more and more of this curve developing in such a way. So the equation is also telling you for a concentration at the specific time, at the specific position, for example, let's talk about here. And the difference between this concentration over the reference concentration C0 over the entire difference is decided by this kind of error function. So if you know what this is the error function used very much in the statistics, and probably I can give you, this is how it looks like. The error function itself is an integral. So it's an integral of such an equation, z to the power of minus y squared. And if you integral this from 0 to z, and you get this error function. So it's quite complicated. You don't need to do the integral itself. And for some common value, you can use the table in the textbook to do or to calculate your concentration at the specific time and a specific location. That's our second equation about diffusion. And the last one is something I think finally you feel a little bit more friendly. I'm sorry about the second equation. This is really something quite difficult, but I hope with my explanation you can sense it. But the third one is very easy. So we talk about two types of diffusion, and I gave you two equations to describe them. Both of them involve a term called D. Yeah? This is so-called diffusion coefficient. And what is designing the diffusion coefficient, right? So this is the very familiar equation. You're seeing it for the third time. If I'm not mistaken, you're seeing it for the third time in our course. You probably see it before as well. So this is an equation very valid when anything is involving temperature. So the diffusion coefficient is a function of temperature. So with such a description, basically it tells you when the temperature is higher, you will have higher diffusion coefficient. So that's something you should understand. This is how it looks like in curve, either D and T, or the logarithmic form of D and 1 over T. Basically, it tells you when you have absolute zero, so the temperature with the unit as Kelvin. When you have absolute zero, you have no diffusion happening, nothing. Everything is ideal, everything is perfect. But once you have a little bit temperature, things are not that perfect anymore. Yeah, the final diagram I want to show you before we go to break is here you can see the description. This is what people measured. The description of the diffusion coefficient with respect to 1 over T, of course. So you can see the carbon in alpha ferrite. So alpha iron is ferrite. You will learn what that is. And is much higher, let's say the aluminum in aluminum or iron in iron. So as you remember, probably this is the so-called self-diffusion realized purely via vacancy diffusion. And this one is realized by interstitial diffusion. That's why I'm telling you the second one, the interstitial diffusion, is way faster than the vacancy diffusion. I mean, you don't see it from the curve because this is in steel. I mean, I'm telling you the D, but the scale is in logarithmic scale. So the difference is several orders of magnitudes. All right, I think that is all for our first session of today. I think I gave you one definition, which is diffusion, and 2 mechanisms, and 3 equations. So hopefully that helps you to understand better about diffusion. Now let's go to break for, let's say, 5 minutes, a little bit more. Let's come back at 11:15, okay? So I hope everybody's back. And now let's take our second concept of today, which is about the phase diagram. So finally, we're talking about phase. The phase we have been talking about since probably the first week on other lecture or exercises. Now let's finally get to it. Okay, let me get my computer moving. All right. So a small introduction, as I always do. So guided by a few questions which have just learned about diffusion. So now you finally understand when we have atom A and atom B, when we just combine them, what will happen? They would start diffusion, right? And we only talk about really some ideal or extreme cases for you to be able to apply the few equations that you can describe them. But in reality, we always know when you try to diffuse A and B or combine, two atoms together, they will finally reach a equilibrium state, right? The equilibrium state is basically you have equal A and B concentration to a certain extent, yeah, not in terms of quantity, but in terms of certain, let's say, rule, a equilibrium. And now we're going to know what are these equilibrium states and what are the controlling factors for these equilibrium states. And more precisely, if we specify you want to mix certain fraction of, let's say, copper and nickel, it can be anything, so two solid solution, two solids, and at a certain temperature, you probably want to know how many phases will form. So here we are already talking about phases, and what is the composition of each phase and what is the amount of each phase. So this will be, let's say, the guiding questions for our lecture about the phase diagram. So you will be able to, after the lecture, so once again, a lot of new terms. Hopefully they will trigger your interests to really get to know about phase diagram. So you will be able to schematically sketch, so isomorphous and eutectic phase diagrams. So I know they're something completely different from what you have learned so far probably, but believe me, after 45 minutes, you will know everything. And then if you're given a binary phase diagram, you will be able to determine phases and the composition of each phase and mass fractions of each phase. Sounds pretty good, yeah. Even more, given a binary phase diagram, you will be able to locate all the eutectic, eutectoid, paratectic, and congruent phase transformations and write reactions for them. So maybe I will get later, but I think there's someone from Greece or has the mother tongue of Greek in our course. That will be, several of these terms actually come from Greek. So we probably try to get in touch with, I think it's Niklaus, right? Is he here today? No, maybe later. So this is the third thing. So you will learn all of this. At least if you don't remember what knowledge about, you at least remember a few Greek words. And after that, you will be able to finally with a specific iron carbon alloy. So iron carbon alloy is just a more academic or scientific speaking of all the steels or steel related products in your daily life. Yeah. So instead of call steel, if you just call, I'm going to take my iron carbon alloy made knife, then you will be someone who learned phase diagram. Yeah. With such an alloy, you will be able to specify the hyper-eutectoid and hypo-eutectoid and a hyper-eutectoid. And you also be able to compute the mass fraction of the pro-eutectoid phase and pearlite. Finally, you can make the connection between of all these phases with your microstructure. Yeah. If you just remember what we have been learning so far about phases, about processes, is finally to be able to make the connection between processes and microstructure. Then we can really get our puzzles solved. Okay, that's enough for the introduction. And let's start with the phase diagram. So I think the easiest phase diagram, although you don't have a really clear definition about phase yet, it will be given in just a few seconds, a few slides. I think the easiest phase diagram you can think about is related to water, let's say. And to be more precise, this is a unary phase diagram because we only have one, let's say, component, which is water for liquid, and then for solid ice and for let's say, gas form is vapor. How this diagram looks like, you can see we have basically three phases in the three forms of water. And you know, although without a very precise definition, you could understand these are three phases of water, right? And these phases are decided by temperature and pressure. Yeah, so temperature is clear because that's what we're doing every day, right? You're having ice for your drink, you're having water, and you try to boil it when you cook something. And let's just talk about at our normal pressure, which is 1 atm here. We have the transition from solid to liquid at 0 and liquid to vapor at 100. Yeah? So these lines are indicating the change of the phases, basically. Of course, if you have higher pressure, you will also change the temperature when you change these phases. Yeah, this is, I think nowadays everybody is expert in cooking, more or less. You probably have the experience with the pressure cooker. And that is how you can make your food faster when you have a pressure cooker, right? Because you basically increase the boiling point of your water and you can reach a higher temperature before all your temperature goes away to the air. All right, that's enough for the very basic unary phase diagram. And now we're going to move forward with a binary phase diagram. So as the term indicates, we're talking about two components. So again, we're giving you a very daily life encountered case. It is the water with the sugar, or you can also call it coffee with the sugar. So basically, we're trying to mix these two. And already I mentioned a few new terms. So mix, yeah. So basically, when we have two components, let's say here, this is going to be not just one kind of phase. It's going to be more complicated. And basically, let's say we again only look at temperature, and it is under the room or normal pressure, let's say. We go, for example, with the room temperature here. You start with the pure water and you start just add sugar into it. And you will see after you add it to a certain percentage, at room temperature, it's 65 to be more precise. It's right there. You cannot add any more sugar, yeah, because before this, if you add sugar into it with a little bit mechanical load into it or some time for that to allow the diffusion happen, you will basically see all your sugar dissolve into the water. So it becomes one unique phase. Yeah, this is called liquid solution. Yeah, so it's called a solution, and because the general form is liquid, it is a liquid solution. It is still one phase. We even have, you know, it's the shrub. But after the 65% of sugar, you find out your sugar will not dissolve anymore. So the diffusion will not just happen as we wished. Yeah? It is becoming a two phases. Let's say it's becoming the liquid solution. Yeah? That's you have as always. And then you have your sugar, and the sugar is staying as solid. If you want to do this at home, I think you can try it. Yeah. You will have now two phases, the liquid solution plus the solid sugar. They're clearly two phases. You still don't have a definition yet, but I will just give you in a minute. The most important concept here is this line. So this line is so-called solubility limit. Yeah? This line is indicating the maximum concentration for which only one single phase solution exists. Yeah, so after this line, you will not be able to form a single liquid solution phase. You finally becoming a mixture. So this is the second term. What is mixture? So mixture is a term indicating you have more than one phases existing. And if I ask you at room temperature, what is the solubility limit of sugar in water? So then you can just read from this line, it's 65%. Yeah. Good. I think that was clear for everybody. Yeah. What you can further read from this diagram is you can change it. Yeah. You don't dissolve 65 or more than 65% of sugar at room temperature, but what you can do is you just elevate your temperature, right? If you just remember what we learned, by elevating temperature, you will you will be able to promote diffusion. Yeah, the diffusion rate will be faster. That will bring up your solubility higher also. So you will be able to dissolve it with just a little bit higher temperature, and 60 and so on. Of course, you will be able to dissolve more, but still there's still a limit, and you can overcome by a higher temperature and so on. So this is how you play with this diagram and how you play with the solubility line. All right, that's enough for water. Now let's come to the business. We're talking about solids. We're talking about metals. Now let's look at a copper and aluminum. So you're now mixing copper and aluminum, and you want to see how many phases are there, what is the differences between that, one phase to another. So finally, now I can give you definition about, first of all, is a component. So the component is referring to the elements or compounds which are present in an alloy. So basically here we have aluminum and copper. So these are the two components. And finally, what is a phase? So phase actually is referring to a material region, material area, material volume that exhibits a homogeneous physical and chemical properties. So I'm saying a little bit differently, but you should be able to understand. So that is referring to the homogeneous material with the unique, with the common or mutual physical and chemical properties. Yeah. With that, I think you can understand when we just mix copper and nickel, copper and aluminum, you will get even visually. Now we're not talking about physical chemical, but even visually you see there's one light and one dark. And so these are clearly two phases. The lighter one is so-called beta phase, and the darker one is the alpha phase. So these are two solid phases. Yeah. And what are they inside? So they are not just purely copper or purely aluminum. Actually, they are a solid solution. So it is copper in aluminum and aluminum in copper. So it's a solution, it's a solid solution. You will see more about this microstructure later. So here I'm just trying to give you the concept of these two important definition, components and phases. So finally we know what phase is. And then you probably is wondering, how is the solubility? What is defined by that? The finally decisive factors for the solid solubility is coming from three factors. So we'll not give quantitative equations here, just some qualitative understanding. So the solubility will increase with the similarity about these three features. If you have a common crystal structure, so both FCC, for example, it will promote the solubility. And if you also have a similar electron activity, that will promote the solubility as well. The last thing is about the radius. If this radius is similar, that will also be promoting. So as you can understand, the maximum solubility is just, you can totally be solute into each other. So that is even something sugar and water doesn't manage, but for some atoms they could manage. I'm going to show you right now. And with this slide, I also gave you the definition about phase diagram. So phase diagram, you have already seen all the figures, let's say, from the water one. They're called phase diagrams. So I'm only giving you a phase diagram that we are referring to in our lecture here. So we're using phase diagram firstly to indicate phases as a function of temperature, composition, and pressure. But we usually neglect pressure in our course, at least. We don't talk pressure, and the pressure is always the ambient pressure, so it's 1 atm. And for our course, we're also talking about mainly binary systems. So you have only 2 components, not more. Of course, you could have more. Yeah, that will make the phase diagram much more complicated. But if you know how to read a binary phase diagram with a little bit of effort, you'll be able to read multiple components diagram, phase diagram. And that's the definition of phase diagram in our course. And here I'm showing you a copper nickel phase diagram. And this is a phase diagram that the 2 components can be completely soluble to each other. So what does that mean? It means from 0 to 100% of nickel into copper, you will form a uniform phase. So it either liquid completely, so from 0 to 100, and of solid from 0 to 100. Yeah, that's the definition about the full solubility. And with that, you can also see we have 3 different phases. So instead of what we have with the water, so for water you have liquid water and you have solid ice. You don't have anything in between. Yeah? But for this 2 component case, you always have something in between. So you have something that you have at that temperature or concentration, you have both liquid and solid together. So that's not be possible to have just one of them. And this line to distinguish between, this is the one component or the solution, either liquid or solid, is called liquidus line, and the other one is called solidus line. And the gap between those 2 lines, this mixture phase, right, is the liquid plus solid. So this is the mixture phase. So in total, we have 3 different phases from this diagram. So liquid, mixture, and solid. So solid is alpha solution. And I have been already speaking about what is so-called isomorphous binary phase diagram. So isomorphous binary phase diagram is exactly what we're saying here with the copper-nickel diagram. So first, the binary meaning 2, that's clear. And isomorphous means your 2 atoms, your 2 components can be fully dissolvable, fully soluble into each other. So meaning your phase is extending from 0 to 100%, either liquid or solid. So that is easy to understand for this isomorphous binary phase diagram. And now we will be able to see what can we do with the defined phase diagram. We have basically 3 functions of the phase diagram. The first one is very, very simple. So I don't think I really need to tell you, but just to make it clear. So meaning if you know a temperature and if you know a concentration, so you know at, let's say, what is example here? Let's say we have a temperature at 1100 degrees C and you have 60% of nickel and 40% of copper, and you want to know what your material will be. So with this phase diagram, it will tell you you have a alpha solid solution. It's a FCC solution. Yeah. And of course, if you go to a little bit higher temperature and with the less nickel concentration, 35%, you will have the mixture phase. It's a liquid L plus the solid alpha. So this is a mixture. And okay, we don't have one more case, but you know how to do that. So that's the first application of phase diagram. The second one is if you happen add into a mixture, or it can be also if you have a solution, and you can really determine what is the composition of each phase. Yeah, I mean for the solution, you know it's 100% of the solution that you have. But if you are in a mixture phase, let's say we have the concentration of a composition of 35% nickel, and we have a temperature at high, it's A, so it's 100%, of course. And this is really too simple. Let's say D is 100% solid. What is interesting is this B point. So when you have the temperature at 1250, you have both alpha and L, liquid and solid. What are they? So they are liquid and the other is solid, but you don't know what they are, right? So if you just read it from your phase diagram, you will be able to determine the liquid that you have. The liquid solution is a solution with 32% nickel, and your solid solution is a solution with 43% solid solution of nickel. So this is what you can use as the phase diagram. So the overall, as you can see, the overall is here is 35%. And this line, by the way, is called tie line. Why is that? Because we're going to use it in the later function. Now you know what they are. So in your mixture phase, you have, okay, a certain percent of liquid solution and a certain percent of solid solution. And I want to know how much are they, right? Because I want to get some quantities. That is the third function of phase diagram. Before I tell you how that is done, you probably can also imagine this is something we're going to use as a lever rule. I think you're not so, you should be very familiar with this kind of case, because basically we have a balance here. The balance is with the C0, 35%. And then you have one phase, which is a little bit far away, and we have another phase which is a little bit shorter to the balanced one, and you want to know how much the weight of this one and that one. So a very clear analogy is what you have is teeter-totter. Yeah, basically we have a balance and we have the distance, which is measured here, so-called S and R, and now you want to know what is the weight of alpha phase and the liquid phase. So you will easily get such equation as the mass times also the distance, yeah, and it will be equal to each other from both sides. This is the so-called lever rule. I think everybody is familiar with this. And basically with this equation, you can write the equation how you want to determine the volume fraction of your weight fraction of your of your liquid and solid solution. So if we just talk about the weight fraction of the liquid solution, it will be, of course, the mass from the liquid over the all mass, and by applying lever rule, you will be understanding it is for the liquid phase, it's the S over the S plus R, right? So just to do a little bit math, you will see the S is calculated as the composition alpha over the C0, the composition of overall, divided by what? The the total, the sum of that, it is the C alpha minus the C liquid, right? So then you get the weight fraction of liquid, and by applying the same rule, you will get the weight fraction of alpha, or you just use 1 minus WL, you will get the W alpha. All right, that's the lever rule, and now let's try to use this rule to calculate, of course, the interesting phase is the B point. Yeah, you just use what we just derived, you will get the weight fraction of the liquid will be 73%, and the weight fraction of the solid solution is 23%. Yeah, I think this is clear to everybody. This is important, although very, very simple, but an important knowledge for you to get, to be able to use the phase diagram. Yeah, so if you have questions, you can ask at the moment. All right, I think everybody is there. Now we're going to move forward. We have spoken about the definition of phase diagram and the related concepts, and you also know what we can use about the phase diagram. So now let's make some connection between the phase diagram and microstructure. So to be honest, this is already a little bit beyond the phase diagram. This is more about process, because what I'm going to show you is a process so-called solidification. So basically, let's start with this 35% of nickel in this copper. And we start with a temperature, let's say it's 1300. And at this point, you have a uniform liquid solution of nickel in your copper. And if you just cool it down, so you cool it down with very slow cooling rate. So basically you just cool a bit, you hold, and you cool a bit and you hold. So you always reach a equilibrium phase, equilibrium state. You will see when we enter the mixture phase, that is the beginning of the formation of your solid solution, is the alpha phase. So at this point, basically you will see what is happening. What is happening is you will have more and more nickel into your solid solution and less in your liquid solution, right? So this is a process completely driven by diffusion. Yeah, but the diffusion is happening in a way which is a little bit against our common sense, because the nickel is going from, let's say, low concentration to high concentration. Yeah, so this is what is happening. You will have the formation of the solid, which is, let's say, 40%. In our position here, you will form the 46% of nickel, and then you will form also the 35% of nickel as a liquid. If you continue cool this down, you will see the solution in the composition in your solid solution is becoming less, and the solution in your the composition in your liquid solution is also becoming less, but the volume of your solid is becoming larger. Yeah? So that is because you need to always make the mass balance of 35% of nickel in the whole mixture, and so on. So basically in this process, your solid solution, which is the alpha nickel, is getting bigger. So it's growing. Yeah, at the beginning, they're just a little bit solid in your liquid solution, and then it's getting bigger and bigger. Now, finally, if you just enter the temperature below, I forgot what is now. So that, let's say now it's 1150. and you end up with the complete solid solution. This is the 35% of nickel solid solution, and finally you become something you're familiar. Yeah, it is the grains and in a crystal structure. So this is the process of basically solidification and related to the microstructure evolution of this whole process. Yeah. I hope that was easy for you to understand. And as I kind of emphasized, what we're saying there is we're talking about always equilibrium structure. You're doing it in a very, very slow motion, slow way. But in reality, you don't always wait for such a long time for your diffusion completely happens. Yeah, so in reality, what we would usually have, instead of a uniform alpha phase of your copper nickel structure, you actually have usually a faster cooling rate. With that, basically, instead of becoming uniform, you will have a chord structure. As I told you at the beginning, you will form a solid solution with 46% of nickel in your solids solution. And then when you just cool it down and down, this solution concentration becomes smaller and smaller. And in the end, so the final layer of your solid will be even less than 35%, because in the core you have more. And in total, you want to remain the kind of mass balance, so you will have to be less at the outer layer. Good, I hope that is clear. This is the reality when you have your solidification process. Excuse me. Okay, I think that was more or less all about isomorphous binary phase diagram. Now we're entered to a little bit complicated, which is called eutectic binary phase diagram. So let me ask if anyone knows Greek. If you know, please make some noise. Let me hear you. So probably no, huh? I remember. Okay. Nobody. Now you have to trust me. So first, let's talk about what we are seeing here. Here I'm giving you not a copper nickel anymore. It's a copper silver phase diagram, so still binary. And what eutectic means. So eutectic actually in Greek means easy. So eu means easy and well. And the tectic means melt, to melt. So the whole word means to easily melt. So in our context here, the eutectic means for a phase diagram, for a two-component phase diagram, we have a minimum melting point. And this minimum melting point is called your eutectic point. The temperature here is called the eutectic temperature, TE, and the composition here is called the eutectic composition, CE. So this is very important. So why we're having such a case, actually the driving force of it is you don't have 100% soluble case for your two components, because you will see we have on the left hand side we have alpha. So here you have your copper, your silver completely dissolved in copper, and on the right hand side you have beta, which is your copper completely dissolved in the silver. But in between, they don't dissolve within each other. So you don't form a uniform solid solution anymore. Instead, you will always have alpha and beta. They're just kind of mixed with each other, and that is a mixture phase. Due to this case, and you will get also a minimum melting point, which is this eutectic. Yeah. So in total now, instead of 2 phases, you have more, but you still have 3 single phases. In the past, we always have 2 single phases. Now you have 3 single alpha, beta, and liquid. And that is alpha and that is beta. And I introduced you the eutectic point. What I didn't introduce you is so-called eutectic reaction. So what is that about? That means at this point, the eutectic reaction, at this eutectic point, when you just cool it down, you will come from a liquid phase directly into 2 solid phase. The same applies backwards. If you just heat up from this eutectic point with these 2 phases, 2 solid phase, you will directly come to 1 liquid phase. You will not enter a mixture. So if you just shift from this eutectic point to either left or right, so when you just heat up a 2 solid phase, you will first enter a mixture phase, which is the liquid plus alpha, and you can go to the liquid phase. Yeah, so that is the distinct point about the eutectic point. So this reaction is only applied to this point. Okay, I hope now you get it. So you get the eutectic point and all the related concepts and definitions. And now we're going to give you some examples. So first of all, so I'm switching a different system. It is lead and tin, but it is looking exactly as the copper and the silver phase diagram. If you just imagine here, you have your eutectic point. I didn't draw the full diagram here, but you can imagine the eutectic point is right there. So first, let's start with a rather low composition of tin in your lead, and so let's say below 2%. Here we will start also from a higher temperature, around 400, and you just cool it down. You will see first we start with the uniform liquid solution, and then just pay attention. There's a very little gap here, and this is the mixture phase. It's L plus alpha. So this is the liquid plus the alpha phase, the solid phase. You will see the nucleation of your R phase, your liquid, and if you apply the lever rule, you will know what is what. And soon after that, you will enter a uniform solid solution, which is completely alpha, and that's it. If we now move to a different composition, let's say now we move to something between 2% and 18%, and somewhere here, if we do the cooling down, we'll start again with the liquid phase and the nucleation of alpha and completely alpha. But if you just go further, you will start the nucleation of your beta phase. So beta phase is on the other side. Yeah? The beta phase will just be nucleated homogeneously, basically, if it's a equilibrium case, and within your alpha, yeah? And they will just grow and until you go to the final temperature. So the interesting point is not those two, and the interesting point is absolutely the eutectic point. So right there, what will happen? So I'm directly showing you the results. We start from the uniform, and when you just enter here, so very quickly, it will form a laminar structure as alpha and beta. So this is a very unique feature about this eutectic point. So you always have a layer between alpha and beta and alpha and beta. And in the end, you can also apply the lever rule to calculate what kind of alpha and beta you have, weight fraction. And this is schematic drawing. This is how you would look like under your SEM or LOM, the microstructure. So this is the eutectic microstructure. Yeah, you can see this is one is layers alpha and one layer is beta. Okay, and if you try to understand how this is formed, and this is what it comes. So it's driven by diffusion again, and you start with a small layer, and it just goes try to conquer all the liquid phase. Yeah. Now you kind of formulate this laminar structure about this eutectic phase. And the fourth point about this eutectic system is, again, two new concepts. All right, I think we're almost at the time. I will finish this slide. And before we finish, I want to introduce you. If we go to the left-hand side of the eutectic point, we will first enter the liquid mixture and liquid solid mixture, and then we have the nucleation of alpha in here. But what is interesting is what happens when after we enter this phase. So as you can see here, almost before we reach this line, this eutectic line here, you have your alpha. Yeah, you have the alpha formulated as they are. And when you just enter here, the alpha will stay as alpha, but the liquid itself will become something as the eutectic composition, right here. It is alpha plus the eutectic composition. So this is the main feature. The key point is after that point, the alpha will stay as it is, and what happens is your eutectic structure will just start to form and kind of superimpose on your formed alpha. So based on the formed alpha, you will just becoming like you're cooling down your eutectic structure. Then the rest just comes. So this is a very key point for you to remember for the eutectic structure. And we will stop at this point. We will try to pick up the rest tomorrow. So if you have any questions, please ask. Otherwise, I will see you tomorrow.